Today's lecture is on perturbation theory. Perturbation theory is very important topic in quantum mechanics. It is very important for M.Sc students and also CSIR net aspirants. From this portion we can get the many questions in CSIR net exam. What is perturbation theory? Perturbation theory is an approximation method in quantum mechanics. Now I am taking an example. You can understand from this example what is the perturbation theory and why we use the perturbation theory. Okay, now we know about 1D potential box. Here the potential will be infinite and inside the box the potential will be 0, and this is 0 to A. So we know the eigenfunction is this and eigenvalue is this. I am considering you know the basics of quantum mechanics. If you do not know the basics of the quantum mechanics, if you do not know 1D potential box, what is the 1D potential box and what are the formulas of the 1D potential box, I will recommend you to see those videos, then you can see the perturbation theory. If you do not know about these things, this video is not for you. Okay, this is advanced quantum mechanics. Here now in 1D potential box, if inside the box there is a change in potential, small change, not very large change, this is very small change. So for this case, what will be the energy eigenfunction and what will be the energy eigenvalue? That will be derived from perturbation theory. Now perturbation means perturbation is nothing but a small change or small disturbance in potential. Okay, so in this theory we will deal with the small change in potential. Okay, for this change, what will be the energy eigenfunction, energy eigenvalue? We will derive it from this theory. The perturbation theory is categorized. Perturbation theory is classified into two types. One is time independent perturbation theory, second is time dependent perturbation theory. Okay, in this video I will cover only time independent perturbation theory. Time independent perturbation theory further categorized into two types. One is degenerate time independent perturbation theory, and second is non-degenerate time independent perturbation theory. Okay, if these two terms are confusing you, so I will tell you in short what are they. Okay, now for degenerate. Degenerate means for different eigenvalue for different eigenfunctions you can get same eigenvalue. Here you can see the eigenvalue is same. Okay, and for non-degenerate case, for non-degenerate, here the different eigenvalue for different wave functions. Okay, different eigenvalues for different wave functions. In this video I will cover only the non-degenerate time independent perturbation theory. So let's get started. Non-degenerate time independent perturbation theory. At first, to derive the energy eigenfunction and the energy eigenvalue, at first I will take some assumptions. Okay, what are they? I will discuss it. Okay, now at first, for unperturbed case, what for unperturbed case? What is unperturbed case? Unperturbed case is this case where no change in potential. This is 1D potential box. Okay, no change in potential. Here I am considering this is Hamiltonian, this is eigen function, eigen wave function, and this is eigenvalue, energy eigenvalue. Okay, and for perturbed case, the Hamilton will be changed into Hamilton will be the Hamiltonian of unperturbed case plus lambda h dash. What is h dash? H dash is the a small change, a perturbed term. Okay, it is the perturbed term, perturbed term, this h dash. Okay, here lambda is just a parameter, now why this parameter is introduced? This parameter is introduced for simplify our calculation. Okay, for simplify our calculation. So now this is our eigen wave function for part of case, and also not take 0, we will not take 0. This is eigenvalue for part of case. Okay, these are our assumptions, and here it can be written as, so I will take it, this can be written as h dash h0 h dash. Okay, just I am introducing here a lambda. Lambda is just parameter which is used for the simplify the calculation only. Okay, it is not very necessary, but it is important for our calculation. Okay, so first we will derive first order correction to energy eigen value. Energy eigen value, this is our goal. In this video we will see it first. Okay, so we know about for know this, we all know this. Here I have done a mistake, that is there will be an n for n state. This represents the state and this is represent the order. Okay, I am taking this is 1, and for part of case that will be h psi n, not I will take not the 0, that will be en psi n. This is 2, equation 2. And we also know about the h equals to h0 lambda h dash, this is equation 4, and en is represented as unperturbed eigenvalue plus lambda first order correction to energy eigenvalue, second order correction to energy eigenvalue, and so on. That will be psi n. Psi n here it will be this. Okay, similar to energy eigenvalue, this is taking equation 5. Now from equation 2 we can get, from equation 2 we can get h0 plus lambda h dash into psi n. I will take up to, here I have done a mistake, that will be lambda square. Okay, I will take up to this. Okay, I will take up to this. The other portions I will not taking, that will be very large and that will be very long calculation. So in short I will take it. Here also from equation 2 we will substitute the energy eigenvalue for part of case, that will be en0 and lambda en1. Here I can change, wait, lambda in1 and lambda square in2, and that will be psi n0 psi n1n lambda psi n1n and lambda square psi n2. Okay, now see this, we will do just multiplication, that will be 0 h0 psi n0 plus lambda h0 psi n1 lambda square h0 psi n2. Just I have done just simple multiplication for these three terms. Okay, now here this 3 will be multiplied by this term. Okay, now lambda h dash h sin s high h dash psi n 0 plus lambda square h dash psi n 1 lambda cube this will be 8. Okay, good. After that I am changing the para, then that will be very good for me. Psi n 0. Okay, psi n 0. Now lambda e n 0 psi n 1 lambda square psi n. Okay, first en 0 psi n 2. For second term, then what will do? Lambda en 1 psi n 0 lambda square en 1 psi n 1 lambda cube en 2 psi n 2, and another three terms are present. Okay, that will be lambda square psi n 2 psi n 0, and that will be lambda cube psi n 2 en 2 psi n 1 and lambda to the power 4. I am doing same mistakes. en1 en2, so you should careful about this because this is long calculation. Now look at this. Here is the lambda present, here also lambda present, and here also lambda present, lambda. Okay, now changing the color. Here is the lambda square present, here also lambda square present, lambda square and lambda square. Okay, now the for zero order, this is zero order, this is also zero order. Okay, now you can see the colors. Let's h n sin h0 psi n 0, that will remain same, and from the yellow color we will take common the lambda, then it will be this. Okay, look at that. Okay, I am doing the color so that will be very convenient to you. And second, the lambda square, that will be h0 psi n 2 plus h dash psi n 1. Okay, the remaining part is lambda cube h dash psi n 2. Now this will be this color. Okay, that will be this color, no problem. After that, en 0 psi n 0 remains same, and here the lambda will take from yellow portion. We can write this as you can see, and last lambda square is taken from the blue colors terms. Here you can see these terms, and last term is plus psi en 2 psi n 0. and the remaining part will be the cube en2 sin 2 plus en2 sin 1 and lambda 4 to the power 4, that will be this. Okay, now from this portion you can see these terms are the common terms. These are the common terms, not these terms are the, okay, that will be lambda square. Okay, now I will not take these violet colors term, because of we will calculate only the first order and second order energy correction and energy eigenfunction, so these are not needed to us. Okay, these terms are not needed. So equating left hand side and right hand side, then we will get H0 sin 0 equals to En0 sin 0. This is question A. Now equating this term and the yellow terms, then we will get sin 1 h dash sin 0 equals to En0 sin 1 En1 sin 0. Okay, that will be B. And the last H0 sin 2 h dash sin 1, that will be En0. Be careful, because of if it is wrong, then whole calculation will be wrong. Okay, these three equations are much more important for the calculation. From equation B we can calculate the first order correction to the energy eigenfunction, energy eigenvalue, and we will calculate it. Okay, from B we can write H0 sin 1 h dash sin 0 En0 sin 1 En1 sin 0. I hope you all know about the Dirac notation. If you do not know, then I will show you in briefly Dirac notation. Now the Dirac notation, what will be the Dirac notation? You can see this is psi, and I will take this, that will be psi star. Okay, this is said bra and it is said Kate. Okay, now you can remember this thing just like this. Now from C you can break it. This is bra and this is Kate. Okay, I hope you know about it. Okay, and I will tell you some properties that is this will be 1 if the two are same. If these two eigenfunctions are not same, then it will be 0 orthogonality, and if that will be, this can be written as psi m that will be del mn. This is known as the Kronecker delta, and this is called the orthonormality condition. And orthonormality condition says that if m equals to n, then del mn equals to 1 and del mn equals to 0 if m not equals to n. Okay, you have to remember these three things. Okay, and I hope you know about the Dirac notation. I have revised it briefly. Now it can be written as using the Dirac notation just like this. Okay, it is not very difficult because of not very hard calculation. Okay, here I can operate with I will operate with psi n 0 in the whole equation. Okay, operating psi n 0. With bra notation. Okay, that will be psi n 0 e n 0 and psi n 1 plus psi n 0 e n 1 psi n 0. Okay, now look at this. Here, if we know about it, H0 operating with this, then we will get this. We all know about it. So here we can write this thing. Psi n 0. Okay, psi n 0 not, that will be e n 0. Okay, please ignore what I am saying. I am saying some wrong things. Please consider it. And here also it will be remain same because of it will not operate with it. And here I can say this is just a number, so it will be come out from this notation. So we can write this is like this. Okay, and it also same thing here also. That will be this. So another thing I have to do, that is the first term will be like this and the second term will be remain same because of this h dash is not operating any function. And I have told you that if the psi and phi are the two different types of wave function, then for the orthogonality condition we can say it is 0. So here this will be 0. Yes or no? Okay, wait. That will be 0. And here also I have told you that if psi and psi, they are both same, so the from the bracket notation and direct notation we can get that it will be 1. Okay, that will be 1. So we can write just E1 1, first order energy correction, first order correction to the energy eigenvalue. Here also you can say that will be 0. Yes or no? Because of the both eigenfunctions are different, the wave functions are different. So our final result is, this is our final result. This thing is the first order correction to the energy eigenvalue. Okay, I hope you will learn these things in this video, and it is very important for M.Sc students. It is the first order energy correction, first order correction to energy eigenvalue. Okay, now we will derive the first order correction to energy eigenfunction. This is also very important. Okay, see this and stay with me, then you will understand the calculation of the first order correction to energy eigenfunction. Okay, so at first I am talking about the first order energy eigenfunctions. We can write it with the summation Cm nth order, and that will be psi m 0, and okay, we can write it. It is known by us because the wave functions are the linear combination of the wave functions. You know that. This is not very much difficult. So now what will you do? We will take the first order equation, which is this equation B, which is equation B. Okay, we will write it. Okay, from there we can say this equation. Okay, this equation H0 Hn1 H dash N0 psi n0 En0 psi n1 En1 psi n0. Okay, now I am writing again H0 psi n1 dash psi n0 by the direct rotation we can say this Yes or no? Yes. Okay. After that, we will substitute the psi n1, the first order correction, into this equation. Then we will get the psi m n 0, that. Okay. Now this term will be remain same, because there will not change anything. And here we can change this term by this. Okay, I am substituting this value into this, and the second term will be remain same. There will be no change anything about it. Now for our calculation, here I will operate a function weapons in the state like this. Okay, for our calculation. Without this we cannot derive the eigenfunction, first order correction of eigenfunction. It is very difficult to write and tell everything. Okay, but for you I will do everything which will be your okay here. Okay, cm, good. Now last term, which will your beneficial. Okay, I will do everything which will your. Okay, now these terms. Okay, good. From here I can take the summation out, and also a0 operates on psi m, then that will be psi m em, and the summation remains same. Okay, I am taking the summation remains same because the next line I will take it outside of this equation of this term. Okay, that will be the same, there will be no difference. Good. And here also same thing, the energy eigen value, it is only a number also, so we can take outside of it, and also we are taking the summation outside. Good. Here I have done a mistake, that will be operating psi en 1 psi n 0. Okay, ignore it. Now after that it will be written as psi n 1 ek 0 and psi n 0 also. Okay, here also I can take these two terms outside of the summation, outside of the bracket notation. Here no change, here no change. Okay, all those things are written properly. This is very important, because of if you do not pay attention to do it, then see, if you do not pay attention, there will be very high chance to get mistake, and to do mistake everywhere, in every term. Okay, now I will consider if k equals to m, then what will be the value. Here also I have taken wrong e m 0, that can be written as en 0. Why I have done it? Okay, m is on the summation, so we can write em as a k ck 0, ck 0 not y 0, that will be n ek 0, and that will be this. Okay, now in those terms I will not change anything, that will be remain same. Here also change will be applied, ck n, that will be k0 and k0 also. Here also we can write this term. Okay, by this we can say that ck n ek0, that will be del k, and okay, I will do it directly. Okay, then it will become 1, that will become, what have I written, that will be 1. Okay, I am not taking anything, and this will be remain same. Here you can see ck n, and this will be also 1. Yes or no? Yes. Here that can be written as en1 psi k0 and psi n0. If we consider k not equals to n, then this term will be 0, and we can write here ck n en0 ek0, and that will be psi k0 h dash psi n0. From this you can write this term like this. Okay, then we can say that the first order energy correction will be written as ck n psi k not. Yes or no? We can take also m also, no problem. Here you can take the k equals to m also, no problem. Okay, it can be written as by also m. I am taking k. Okay, psi n 1 equals to psi k0 h dash psi n0 by en0 ek0, and that will be psi k0. Okay, this is our first order correction to energy eigen function. Okay, you can write it in your notebook. I hope you have understand all the concepts and all the derivations. Okay, now okay, it is enough for today. I will cover the second order energy second order correction to the energy value in next class. Okay, so thank you so much. And in this video I have done lots of mistakes, so please consider it. I have corrected after some steps, so it is very long calculation and huge calculation, so please consider it. Thank you so much for staying with me. I hope you all understand all this theory. Okay, next class I will discuss about the second order correction to the energy eigen value. After this, good luck.